Hello, good morning, good evening, good afternoon, people. Welcome to another episode of Yogabyte DB Friday Tech Talk. This is a series by engineers for engineers, and I'm happy to be hosting today's talk. My name is Kannan Muthukarupan. I'm one of the co-founders at Yogabyte, and it is my real pleasure to welcome Patnaik, who is our speaker for today's topic. So Patnaik, welcome to another episode of YFTT Tech Talk. And by the way, before why don't it would be great if you can briefly introduce yourself. And I did have a question for you before we get into the topic.
Yes, so I'm Patnaik and I work in the transactions team at Yogabyte. So I think about like safety and performance every day, and it's been like super interesting so far. So yeah, that's my background, and have been here for like 9 months at Yogabyte.
Wonderful. And my question was on your LinkedIn profile, it says move fast to slow time.
Yes.
Is that
Yeah, that's
something you had from a long time, or it's related to the area that you've been working on recently?
yeah. So I have been thinking about timestamps for too long, but that's a relativity joke that you can. If you move quite fast, you like time is relative. So
Nice.
it's kind of a relativity joke. Yeah, I'll get started.
Please.
So yeah, today I come to you guys with a fundamental topic about distributed systems, about timestamps, right? And today we are going to talk about what retries are and why we need them. We'll discuss an example scenario with retries, and we will discuss Amazon Time Sync service, what that is, and how that can help us eliminate retries, right? So let me dive in. So this is mostly about transaction ordering stuff. So coming to an example, right? Say we have Alice who is depositing $100 into her bank, right? The bank records this deposit into a ledger, and this $100 is recorded as a deposit. And later on, say Alice is going to an ATM and she's checking her balance, right? And her balance must reflect this deposit of $100. She cannot see like $0, right? It should reflect. And what can happen is like banks usually they use a database to implement this transaction ledger, right? So say we have a transactions table here at the top, and it has ID and balance, and the balance is represented as a positive number for deposits and like a negative number for withdrawals, right? And this is like an account ID, and Alice account ID is like 42. So how the bank can implement this deposit and checking process is by having an insert query to the database, right? So this 42 is the idea of Alice, and she's depositing $100, right? And when she is checking her balance, she would sum all the balance amounts for her particular account ID, right? So say she deposited $100 and she withdrew like $50, that will be 100 minus 50, which is like $50, right? So that's how we check the balance.
And just to be clear, so instead of keeping the pre-aggregated total, you're keeping it as a ledger of transactions for each user ID, right?
Yes, and this is for illustration of
Yeah.
when we need retries, when retries may happen, right? And so what can happen right now is right, like the database assigns timestamps to these queries, to these transactions. So if the database assigns a transaction of 110 to insert, and if it assigns a timestamp of 90 to the select, right, then what will happen is that the select does not see this insert because it is being executed before this insert because of the lower timestamp. So in a sense, we are missing this deposit of 100, which should not happen. So the database should detect these kinds of scenarios, and it should make sure that this timestamp is like higher than this, right? And like you might be wondering, like Alice is requesting for her balance after she deposits, right? Like, why is this timestamp higher? It does not make sense at first, but it makes sense when you consider a distributed system, right? So in a distributed system, we have like multiple nodes N1, N2, and N3, and say like the current time is 100, right? So this green digital clocks, they represent like the current time, which is 100. And the thing in distributed systems is that the clocks are not perfectly synchronized. So on node N1, you can see that the local reading, when you read the timestamp from the node, it will be a little bit ahead of the actual time. It can be a bit ahead, and in this example, it is a bit ahead. And on node N2, the clock is a little bit behind, right? So the clocks can like go ahead or like go behind, and this kind of phenomenon is called like the clock skew phenomenon, right? So the clocks are not perfectly synchronized, and you can kind of see where I am getting at, right? How like select can get like a lower timestamp, and we will see that example scenario. We'll revisit that example. So say Alice is inserting the record. She's depositing $100, and the insert goes to node N1, right? And even though she is actually inserting at timestamp 90, since the clock is ahead, it gets a timestamp of 110. And later when she checks her balance, right, uh, it goes to node N2, the select query goes to node N2, and even though like the actual time is actually 100, since the clock is behind, we are picking a timestamp of 90. And this is how select can like get a lower timestamp, even though in real time, like select happened after like the insert, right? And this is this is basically an issue where you are reading stale reads, and Alice will not Alice will not see the deposit that she has, and that's not good, because you know Alice might have like a panic attack, right? Medical bills are expensive as is in US, and yeah, now let's see how Yugabyte handles this scenario, right? Of reordering of timestamps. So what Yugabyte requires is and have an NTP kind of a protocol where the clocks are roughly synchronized. Yes, they can go out of sync for a little bit, but the expectation is that the difference between these clock readings is called clock skew, and the expectation is that this clock skew is within 500 milliseconds, right? So we make this fundamental assumption that the readings between any two nodes is like 500 millisecond at any particular point of time. So now that we have this assumption, one approach Yugabyte could have taken is, whenever you execute select, you pick a timestamp that is 500 milliseconds in the future, right? So if it does that, then no other write that has happened before us will have a timestamp higher than us. That is guaranteed, because the clock skew is not, it's not more than 500 milliseconds. But there's a big problem with such an approach, and that's that the select has to wait 500 milliseconds like each time, and that is not desirable, right? So we take a more optimistic approach in Yugabyte, where we say, we will pick the read time as the same as the local reading, but we will have like a danger window of like 500 milliseconds. So this orangish window is, yeah, you can consider that of length 500 millisecond. And if there are any writes, conflicting writes, so the write should be on the same key as the select is reading, right? If there are any conflicting writes that are in this window, we will do a retry. So what select does is it advances its timestamp past this write time. So that the right is no longer in the danger window, right? So this particular upper bound does not change, but yes, this timestamp may advance past this, right? And when it does that, yeah, yes, it can reread the database. This select can like reread the table and give us a correct number,
So
including this insert. Yes.
given that this is an important point, let me also just re-emphasize this point. So, and by the way, we are still talking about the prior design, and Patnaik is going to get to the newer design later. But in the prior design itself, there were two choices, right? One is to sort of wait out this conservative clock skew on the read of 500 milliseconds, but that is not very performant in terms of latency and scalability. So rather than take that, he made the point that we are taking an optimistic approach, that if we run into records that are potentially conflicting with the records we are modifying, only then we handle this, so that in the optimistic case we don't have to wait out this clock skew. But in a high contention workload, if where the same record that we are reading was recently modified in this uncertainty window, then we retry by taking a better guess of what the read point could be, right? And there's an upper bound to it, the
Yes.
500 milliseconds, but we don't necessarily wait out the 500 milliseconds. If this write happened 200 milliseconds ahead, we will try to reissue the read at 200 milliseconds future point in time.
Yeah, yes, exactly. And to add to your point, since this is like a transactional workload, we do not expect like the select to run for too long. So the chance of insert conflicting with us might be like a little like low.
Correct.
So yes, and there is a main disadvantage with this approach, and that's like 500 milliseconds. It's a bit long, and we will see uh, how that can affect us, right? So even if like the insert did not happen before the select, right? In the before case, in the Alice's case, the insert actually happened before select, so it makes sense for the select to read after insert. But say the insert was issued after the select was issued, right? Even in that case, the select can see a conflicting insert within this danger window. And even in this case, we do a restart, right? And this seems unnecessary, right? Ideally the select should happen as is, but unfortunately the database cannot know if like the insert happened like insert it was issued after us or before us. So the
Yeah.
best thing we can do right now is to reduce like this window. And I can like show you an example where we get this like retry, right? Read restart error. Let me show an example of that. So this read restart error will manifest itself as uh, this restart read required it. So the way it can happen is that if I do like a bunch of inserts, and let me roll this back, uh, and I have a transaction, I have a select, and I do a select constar from keys, right? So if I am doing a long select, there's a higher chance that there's a read restart, and it will manifest as this particular error. I think most users have seen this error when they are using Yugabyte. So this is what we want to like minimize, right, in this project. And for that, we take advantage of Amazon Time Sync service infrastructure. So Amazon Time Sync service, like they provide specialized hardware to us. This is public, this is free, and they provide like GPS clocks and also like atomic clocks, as well as like hardware time stamping support on like network cards and so on, so that the clocks are more synchronized, right? So without like this service, the clock skew could be like 500 milliseconds or something. But with this, the clock skew is generally like within 1 millisecond. That's already like 500 times better, right? Even like 100 microseconds with their latest hardware, 100 or like 40 microseconds. So depending on like the network protocol that you are using for synchronization, right? So like uh, that is good, but we still cannot use the old design. So in the old design, right, we use like we assume like there's a clock skew. Unfortunately, like there are no guarantees on like clock skew. there's no static guarantees on the clock skew. And if you assume like a static guarantee of, let's say, 1 millisecond, right? There's always a chance that some clock on some node is too far from the reference clock, and we are running into inconsistency issues because our right, even though it happened like before us, it's no longer in the danger window, right? If you choose like an incorrect uh, size for the window. I hope this part is clear. So let me know if there are any questions on this one. And so the way we solve this issue is to handle this dynamically, uh, and we take advantage of the ClockBound library that AWS provides us. So they open sourced this library, and this library provides us with an important metric, right? And that metric is how far our local reading is from like the reference clock. So let me recollect again that this green digital clock is like the current UTC time, and it's the same across every node. And this clock is like our local reading. And what we can get from the library is the difference between the reference clock as well as our local reading, right? And that's called like the clock error. And the main point here is that we can only get the clock error of ourselves, right? We can only tell how far our local clock is from reference, like the reference clock. We cannot tell how far the other clocks are, right? And let me tell this with an example. So say on node N2, right? We have a clock error of 10 units from 90 to 100. We cannot assume that the clock skew is 20. We cannot assume that because the clock error on like a remote node can be like 20 units, in which case like the clock skew is like 30 units, right? Because 20 plus like 10. So this is something uh, that makes it so that if you assume clock skew is like 20 units, you'll still run into these inconsistency issues where uh, the select goes through even though the insert happened before us. So how do
Basically,
we handle it?
you're saying you can't just 2x the clock error to
Yes,
say, hey, that's the total upper bound, because each node is getting its own notion of what the clock error, max clock error is with respect to the so-called absolute clock, right?
yes, exactly. Yeah, that's exactly. Yeah, so how do we solve this problem, right, of not having clock skew as 2 times clock error? So we make like a key observation here. So let me recollect this point that if we take a local clock reading, the reference clock is always within clock error. So it is our system time minus clock error and plus clock error is where the reference time like lives. So using this definition, right? We say that you know the uncertainty windows, which is this is called the uncertainty window, and they overlap across the nodes, right? And why is that the case? Because the reference time is common across all the nodes, right? And the
If you
reference
take
time,
if you take every node's min and max possible time,
yes.
because the reference clock has to be in that window, they're going to overlap. Yeah, that
Yes.
makes.
So yeah, the reference time is always the same. So we can use this observation to uh, pick the timestamps correctly, right? Let's come back to the example of Alice where we have an insert and a select, right? So for the insert, we can pick the right time as like the earliest. Earliest is like the least time that can be in this uncertainty window, and we can pick the read time as the maximum time that the uncertainty window can take, right? The reference time can take. So if we pick write time and read time in this manner, right? So we can observe that the write time is like less than the reference time, and the reference time is like less than the read time. So the read time will always be like higher than the write time, which was problematic before because the select was picking like a lower time than the right time, if you guys recall. So this ensures that the consistency is always maintained. But like I'll pause here, and if there are any questions, yeah, you
A few
can.
questions.
Mhm.
One is does the AWS time sync accuracy change for multi-region versus multi-zone setups?
No, so uh, I can explain that again. So the way this time sync service works is they have a reference clock in each data center, right? So a data center, yeah, you can think of it as like a zone. And since I don't know if they have one or multiple, I think they have multiple reference clocks for redundancy. So these clocks are perfectly synchronized. So there is no like cross data center like network connection that is like synchronizing these nodes. That is happening through this GPS. So this GPS and these atomic clocks kind of ensure that these perfectly synchronized. So that's kind of the magic that's happening behind the scenes in the hardware. And the only clock error element happens through this local communication
Got it.
within the data center.
Got it.
So yeah, it's
Understood.
uh, yeah.
And then the other point I wanted to make on your most latest slide is
Mhm.
um, uh, basically like the other observation is like instead of like 500 milliseconds, the previous design sort of assuming that the worst case clock skew was 500 milliseconds. Now it's
Mhm.
a dynamic property. If things are healthy, we'll be operating under a much tighter bound, right? And
Mhm.
but if there is some connectivity issue, then it's dynamically, then these numbers will grow, but the system won't
Yes.
choke, right? I mean, it's more of an adaptive scheme now.
Yes, it is a very adaptive scheme, and yeah, to clarify, like this is in a sense, it's more consistent than the previous design, right? Because yes, 500 millisecond is a very conservative bond, but it can still happen in like very rare cases that the 500 millisecond clock skew is also violated, right?
Correct.
And but this is like a perfect solution in the sense that no, there's no such violations here.
Yeah.
Yeah, and yeah, continuing on. So yes, we can pick read time as like the maximum time reference clock can be. But the problem with this approach is again we have to wait 2 times clock error, and we didn't want to pay the cost. So we wanted to take a more optimistic approach again, right? So this is like the dynamic aspect to our hybrid logical clock that we already have. So what we can do is again pick the minimum time for the read time, and bring back the optimistic approach of having a danger window again. So the danger window spans from the minimum on the select to the maximum of this uncertainty window. And yes, usually the writes do not fall in this window because this window is quite small. But if they do fall within this window, we will do a restart again as before, and that will ensure consistency for us. So yes, this is very close to what we do right now, but we also have so many additional optimizations on top of it, which is not the which is out of scope for this talk, but maybe in some future talk or some future blog can discuss those things. So that's our current design, and if you have any questions, feel free to ask them in the channel. But otherwise, like I will go through how you can use this, right? So this feature, this new clock design is currently in tech preview, all right? And it's available in the latest preview release as well as like the latest stable release. And let me show you how you can configure this clock design, right? So, sorry. Yeah, and for configuration, you can uh, visit this page where you have system config, and go to this page configure ClockBound or and configure precision time protocol, which is available in like latest AWS instances. You have to run a couple of scripts. This requires root permissions uh, because timestamps is like a privileged operation. And you also need to configure the database with this new time source. Okay, and uh, let me show some results too while we are here. So this this is something. This is a workload that I have run before this talk called SQL stale read detector, which is a part of our YB sample apps, which is again open source, right? And I ran this for our old clock design and also for the new clock design, and you can clearly like see the results here. I also log like the number of retries that happen, and we can see that there are 5,000 like retries if you do not use like the new clock design, and if you use like the new clock design, it's much lower, right? And this is also like a pretty stable number. It's not like a single run kind of a thing. I did run it multiple times, and it's kind of reproducible. So this is like a big improvement, and you can also look at its impact on the latency, right? Since we are not retrying it, the latency after will be like much lower, like 130 millisecond, than say here where it is like 870 milliseconds or something like that, just something high like that, right? So
And this what
mhm.
this like roughly how many rows did you have in your table?
Yes, so it's around like 10,000 to 100,000. I don't remember the exact
Sure.
number.
So you
Yes.
had a whole bunch of rows, and those
Mhm.
keys are getting constantly modified by
Yes.
writer thread, a bunch of writers, and then
Mhm.
the read thread is simply trying to do a sum of all the rows, right? Is that
Yes, so yes, exactly. So to describe the workload, it's kind of similar to the example that we discussed in the slide, where there is a bunch of like modifications to the table, and we are doing a sum in the read thread.
and
Yes.
and the intuition basically is like previously anytime we found a potential change that happened within the 500 millisecond uncertainty window, we had to be very conservative and retry.
Yes.
But now the ClockBound library and the Amazon Time Sync service makes
Hmm.
it in the how much, like, would you say 1 millisecond or sub 1 millisecond range? What is the?
Yeah, so in this setup, it's around 150, 200 micros because we yes, like the number that Amazon provides us is like 40 micros, but since we need to calculate clock skew and with our new clock design, it's around like 150 to 200 micros.
Got it. So
Yes.
unless an overlapping write happened in that window of what our select
Mm-hmm.
statements read point is, we don't need to retry, and that sort of explains this
Yes.
significant drop from like 5,000 retries to 3 retries. And I think that counter we are printing how frequently it's like once every 5 seconds in this experiment, like something like. But it anyway,
Yes.
relative number. So
Yes.
yeah, it's really good to see.
Yes, I'm really happy with the results because we have tried many optimizations before, but none of them like come remotely close to what we can get from like the time sync service solution. And it's not just this benchmark, right? We have more benchmarks that I ran. Yeah, like you can see like all across more realistic benchmarks, right? Yes, the benchmark I'm running is simple, but I have also like written some more realistic benchmarks, and you can clearly see a huge like drop in the number of restarts. So again, this is open source. YB sample apps is like an open source repository. You can try it too. So yes, that concludes my talk.
There's one more question,
Hmm.
what about are there any restrictions on where this service is available? And there are two aspects of that. Like, is it something that's available in the open source version of Yugabyte also, or is
Hmm.
it something only for the the fully managed service and so on? That is one angle. The other is, are
Hmm.
there of course, you already said it's in tech previews, but assuming that this question is more around when we roll this out. Then the second aspect is, are there any restrictions on, is it available in like other cloud providers or on private cloud, right? GCP, Azure, and what about on? So if you could answer those.
Yes. Yes, they're both like really good questions. For the first question, yeah, this is like a database feature. So this is open source, of course, and it's available everywhere. Except if you want to use like Gigabyte managed, yes, I mean you are paying for the managed anyway. Yeah, there's no extra cost for this. And coming to like the second question, whether this can be used in other places. So the ClockBound library that AWS provides, right? This AWS ClockBound library, uh, this can work for all like time sync services. So everyone has a time sync service, AWS, GCP, Azure. They all have time sync services, and this ClockBound can run there and give us timestamp. But AWS open sourced this library, and thankfully we can use that library everywhere. And the difference is that not every time sync service will have the same bound, right? Some will have lower bounds and some will have higher bounds, but still it's much better than like say 500 milliseconds, right? And AWS has their PTP service, which they are rolling out. So and that has like much lower bounds, like I mentioned, like 40 micros of clock error that they provide.
Wonderful. And have you had a chance to try this out on any other clouds yet, Patnaik?
Yes, so I tried it out on GCP and Azure. This is still in tech preview, by the way, so it's not you know fully fleshed out, but they work pretty well. So
Wonderful. Um, I'd like to thank everybody for joining us. I believe this is our 133rd episode of the Friday Tech Talk series. And we'll see you on another Friday with another topic. And thank you so much, Patnaik, for talking about a very interesting project that you worked on. Also wanted to take an opportunity to thank the AWS Amazon folks for their collaboration on this and for their fundamental work on the ClockBound library and the time sync service. So
yes,
over to you, Patnaik, for closing comments.
yes, I would also like to thank the Amazon folks because they were super helpful with this project. They provided this ClockBound library, right? They open source it, and they were very responsive, right, with any questions we had and so on and so forth. And this is like a very interesting topic and fundamental too. So it's been great pleasure to work on this project too. Yeah, and I hope, yeah, like the number of read restarts reduce significantly after this. Yes.
Fantastic. All right. Thank you all.